Okay, so here is a limiting reagent problem, and in this problem we're not only given how many grams of each reactant that are initially present, but how many grams of product are produced at the end. So this will actually be a fairly interesting problem where we'll be able to learn the extent of the reaction. Like if it didn't go all the way, we'll be able to tell. And we'll be able to backtrack and figure out how much of a change there was, how many moles actually got consumed. First, let's convert everything, well, first let's make sure the reaction is balanced. So as it turns out it is. If you just check, you'll find that there's 2 oxygens on either side, 4 hydrogens on either side, so this is balanced. Next, we're going to convert from masses to moles. So we use the formula mass, we calculate it using the periodic table, and we get that the formula mass, or the molecular mass of oxygen, O2, is 32 grams per mole. So 64 grams is actually 2 moles of O2. And 10 grams of H2, that is 5 moles of H2. So the molecular mass of H2 is 2 grams per mole. So if I convert 10 grams to moles, I divide by 2 grams, or 2.016 grams, and I end up getting about 5.0 moles of H2. So let's go look at the mole ratio and figure out how many times we could run this scale of a reaction. As written, the scale of the reaction is 1 mole of O2. For every 2 moles of H2O gives you 2 moles of, sorry, I'm messing this up. 1 mole of O2 for every 2 moles of H2 gives you 2 moles of H2O. So if I divide the number of moles of O2 that I start with by the stoichiometric coefficient 1, I end up getting that we could run this reaction at a maximum 2-fold scale. So I could actually have 2 moles of oxygen react with 4 moles of H2O to produce 4 moles of H2O based on the oxygen. That's the amount of oxygen that's there. If we had as much hydrogen as we ever needed, if we had just excess hydrogen lying around, that's how much oxygen could react. That's the scale of the reaction that could occur based on that much oxygen.
So can you tell from the equation up there, just the O2 right there?
We can do the same thing for H2, and if we divide this number of moles of H2 that are present by the moles of H2 that are required, we get that this is a 2.5-fold amount of H2 for this scale of a reaction, right? So we could actually scale this up 2.5 times based on the hydrogen. We can only scale it up 2 times based on the oxygen. So which one is the limiting reagent?
Yes.
Right, the oxygen is what runs out first. The oxygen is limiting this reaction. Now, it's illustrative because if you think about it, there are more moles, sorry, there's more grams of oxygen, right? But it's still the limiting reactant. So you can't just use grams. And even though it happens to be the least number of moles, we still can't use moles by themselves. We have to compare them to the relative amounts that are required by this reaction. So don't compare 2 to 5. Compare 2 to 2.5. Compare the scales that could possibly happen in this reaction. Okay. So in the question, we're also given that at the end of the reaction, whether or not it went to completion, we'll have to figure that out. We ended up getting 72 grams of H2O. So if we convert that to moles, we get, okay, so we can write an ICE table. I is for initial, C is for change, and then E is for end, or for equilibrium amount. And what we start with is 2 moles of H2, 2.5 moles, sorry, 2 moles of O2, 2.5 moles of H2, and, no, I'm sorry, we have 5 moles of H2, right? Yeah, sorry about that. It was 5 moles of H2. And we have 0 moles of H2O to start with. We also calculated, based on the 72 grams of H2O that you end with at the end, that that's 4 moles of H2O. So if there's 4 moles of H2O, and there were 0 at the beginning, that means those 4 came from the reaction, right? So we ended up getting 4 moles of H2O. That means that there is a twofold reaction happening here, right? Because this reaction happened at a twofold amount to end up getting 4 moles.
So it happened twice, and that one with 2H2 just gets thrown away? Or?
Yeah, we'll find out. So if the scale of this is 2 times whatever's in this in these stoichiometric coefficients, then we'd end up consuming 2 times the H2. So that's consuming 2 times 2, that's consuming 4. So we'll end up with 1 mole of H2 at the end. And we'll end up consuming 2 times this 1 mole of O2. So we'll end up consuming 2 moles of O2. We end up getting 0 moles of O2 at the end. So this makes sense because we're pretty confident that the O2 was the limiting reagent. So it makes sense that it's gone, and we're left with some H2 left over. And let's see what the question asks for. Which final mass is correct? There are different masses, some for O2, some for H2, some for H2O. So if I look at this, I know B is wrong because O2 is the limiting reagent, so I really shouldn't have any O2 left over. 73 grams H2O is inconsistent with what's given in the problem. I said that there was 72 grams of H2O left over, not 73, so that's clearly wrong as well. Let's figure out between C and D which one is correct. So now that we have this 1.0, that's a number of moles. So if I want to convert 1 mole to grams, what I will do is I'll multiply by the formula mass. So the formula mass was 2.016 grams per mole. That's H for 1 mole of H2. And the moles cancel. And I end up getting 2.016 grams. And since we only had 2 sig figs, 2 is more appropriate than 3, so D is the best answer. Actually, yeah, I think that's right. So it's a lot of work, but what we did in this problem, in summary, was we made sure that we were working with a balanced chemical reaction. That was the first thing we did. Next, we converted grams to moles. We used the balanced chemical reaction to determine if there was a limiting reagent, to determine how the mole ratios that were given in the problem based on these masses compare to the mole ratios in the reaction. And we figured out a limiting reagent, and from there we determined end quantities in moles, and then we ended up backing out masses by converting those moles to masses using the molecular masses of the different formulas. So if I had a flow chart, what this would look like is once we have this balanced chemical reaction, we go from grams to moles, we apply it to this reaction, and then those give us moles and we go back to grams. So whenever you want to get stuff out of this balanced chemical reaction, or whenever you want to put stuff into it, it has to be in moles. And oftentimes the problem will be asking you stuff in grams. So you got to convert from grams to use the reaction, then you got to convert the moles back to grams. I can't use grams directly because this is not written in mass, it's written in number of moles. Okay.